We're going to be talking about um, the extension of the one-way Anova and the Manova. And what this is, if you'll notice, is that the general idea of the Anova, the analysis of variance, doesn't change. We're still looking at the mean differences between three or more unrelated groups. Okay, the difference between the one-way Anova and what we're calling here is the n-way, but the n-way could be a two-way, three-way, or four-way Anova. Very uncommon to see four-way, and sometimes even three-way. The most common that you will see is application is a two-way Anova. In any event, the one-way Anova, we're looking at least one or more independent variables, but those independent variables only have one level. Okay, so unlike what your book says one-way Anovas only use one independent variable, which is not true. It all depends on the type of design. I'll illustrate that in the coming slides. But it's that you can have multiple independent variables, but they only have one level to each of those independent variables. However, when you're looking at using more than a one-way, perhaps a two-way, you need to have at least two independent variables at a minimum, and each of those independent variables need to each have at a minimum two or more levels. Okay, so what does that exactly mean? Well, as I always have to go back to research design, because it's difficult to describe a type of analysis without giving a specific research design, which would necessitate the use of one of these types of analyses. So if you look at the top right here, we can kind of start looking at the differences between the one-way and the two-way Anova. So the top design looks is more of a experimental or quasi-experimental design. It's a between subjects approach. And we have three groups. Okay, so we have group one receives treatment A, which could be like behavioral therapy. Group two receives treatment B, which could be cognitive behavioral therapy. Treatment three receives group three receives no treatment, otherwise known as a control, and they're all measured on the same outcome, which is the dependent variable. So this is a post-test only three-group design. Okay, we have two independent variables, treatment A and treatment B. Okay, so if you look to the right of that, kind of distinguish all the characteristics of this type of design. There's two independent variables. The grouping variable is three, however, because there's three groups. Okay, so there's three or more means that we're going to look at. So we just use a one-way Anova. Why the one-way? Because our independent variables aren't separated out into different levels. They're unique. Okay, so they only have one level. So there's only one type of treatment A and there's only one type of treatment B. They're not split up into levels. So here's an example of where there are multiple independent variables. You still use one-way Anova. If you look at the bottom right, here's a different example where it would necessitate the use of a two-way Anova. Okay, so in this case, if you notice, there's two independent variables. There's gender, and then there's therapy. Okay, so those are our two independent variables. Remember, you need to have at least two independent variables, and both of them need to be broken up into, at a minimum, two levels. Okay, so our independent variable gender, in this case, is broken into two levels, either male or female. And then our therapy is broken up further into two levels. We'll have intense therapy and easy therapy. Okay, so if you look to the right, to the left, you'll see the distinctions here. We have two independent variables, just like the other design, but in this case, our independent variables are each broken up into two levels. So our first IV, gender, two levels, male and female. Second IV, two levels, intense and easy. And that would necessitate now the use of a two-way Anova, otherwise known as a 2x2 factorial design. Okay, so why is it 2x2? Well, because there's two independent variables, and each one of them have two levels, okay? So if you look in the cells, and they're called cells, you would multiply essentially the 2 by 2, and you would get 4 cells, as you see here. So males, there will be a group of males in the A box who receive intense therapy. And there will be a group of females, indicated as B, getting intense therapy. Then you'll have a group of individuals in the C box who are male and receive only easy, and those in the D box, females, only get easy. And there's no crossover here. This would be otherwise known as a between subjects factorial design, because the participants don't cross over between conditions, okay? There are instances where you can do it within subjects factorial design where the groups cross over and go, but we're not going to go into that here. So essentially what we're looking at is it's a 2 by 2 framework, 2 independent variables, both broken up into each 2 levels. Now you kind of understand when you have this scenario, it would necessitate the use of one of these types of analyses. So let's get away from our visuals and just look at our words. Remember our grouping variables. The grouping variables just defines the groups that are being compared. So in the Way Anova, there are at least 2 grouping variables. And like I mentioned, at least 2 in this case, those would be your 2 independent variables, okay? And then sometimes they're referred as factors. The groups being compared are defined by the levels of each of these factors. So in the previous example, the levels, factor 1 or independent variable 1 was gender, and then the 2 levels are male or female, okay? So we're going to run through an example here where we have 2 factors. One is gender and one is insurance status, or in other words, 2 independent variables. Okay, so here we kind of have the same idea. This is a 2 by 4, 4 meaning that one of the independent variables is broken into 4 levels. This is how the logic works for everything. Gender is always broken up into the 2 levels, which we have male and female. Insurance is broken up into none, Medicare, TRICARE, or private. Now again, like I said, you always multiply the 2 levels of the independent variables. So if we multiply 4 times 2, we get 8, which means we're going to have 8 cells or blocks from which we will run our analysis. So block A, males will be tested with or looked at as those who have no insurance. Block B would be females with no insurance. Block C would be males with Medicare, and so on and so forth, okay? And as it notes here that each study participant is in one and only one group, okay? So the 3 sets of means will be compared, which are the mean number of visits in each of the 8 groups. We'll call this interaction effect. I'll explain that in a minute. The mean number of visits for each gender and the mean number of visits for each type of insurance. Okay. The characteristic of interest, usually in this case it will be our dependent variable, and our dependent variable in this case would be the number of visits. So this is basically our outcome variable. So here's our general or overarching research questions. The mean number of medical doctor visits made in a year affected by gender and insurance type. And really, when you break it down into this factorial design, really 3 questions start to emerge. So we have to look at each combination separately. So it's the mean number of physician visits differ for the different levels type of insurance. And then we want to look at it by the different levels of gender, whether you're male or female. And then we want to look at our interaction effect, like I said earlier. It's the 3rd piece to the equation that the that the factorial design will look at, and now the two-way Anova will give us. Is there an interaction effect from the intersection of type of insurance and gender on the mean of the, well, they say dependent variable, but really the number of visits. So in other words, and I reworded it here, does the difference in the mean number of visits, is there a difference in the mean number of visits between those with different types of insurance that vary based on their gender, okay? So our grouping variable is gender, 2 levels, insurance, 4 levels. We went over this. And then our dependent variable is our number of visits made in the past year. So what it's going to do is it's going to compare the means of the 4 or more independent groups defined by the 2 grouping variables. In this case, there's 8 different cells that it's going to be looking at. This is a parametric test, so we're going to assume that there's a normal distribution. We're going to assume a homogeneity of variance between the groups, and it's going to look at the mean and standard deviations for each of the levels in each factor. Okay, so our question would be, how many groups are defined by the variables gender and smoking? Okay, so in this example, we have gender, which is 2. We have smoking, which is 4. 2 independent variables. This looks like a 2 by 3 because smoking is broken up into 3 levels: never, former, or current. So 2 times 3, which means basically simple math, that means you will have 6 different groups broken up and looked at via the analysis. Okay, so we're going to go back to our original 2 by 4 factorial, and we'll look at 108 randomly selected attendees. They took a short quiz in which they were asked to provide their gender, type of health insurance, and number of visits they made to a medical doctor. Now, just by this scenario, you can tell this is not any type of experimental or quasi-experimental design. It's just a basic cross-sectional survey approach where they collect all this type of data. Then you'll use some type of statistical procedure to go and control the data, break it up into different levels, and then analyze it utilizing the two-way Anova. So there's no scenario where they're set up into different conditions, the independent variable is manipulated in any type of way, and then tested post-test following the introduction of the independent variable. So in this case, we're really not looking at cause and effect per se. This is very much non-experimental. So our hypotheses, we always state our null and our alternate. And as you remember, our null is basically, doesn't matter what type of insurance, we're just not going to see any differences, or all the groups are at least equal. Alternatively, we would say one of the 4 insurance groups has a different mean number of visits, and they would be statistically different. And then for gender, our null would say that there's no difference whether or not you're male or female, it would be equal. However, alternatively, we would say the mean number of visits will differ by gender. So we go and run our statistical analysis to confirm or reject or refute these hypotheses. And we also have to include our interaction. There's no interaction effect of gender and insurance type on the mean number of visits. And then, of course, alternatively, we would say there is an interaction. We always said for these examples, our alpha level at 0.05. So here are the assumptions, assuming, it follows a parametric assumptions of normality. Study participants constitute an independent random sample. Okay, so there was no interaction or dependence between each of these study participants. And mainly the way to control through that is through the methodological technique of random selection. Okay, so each person had an equal opportunity of being selected to participate in the survey. The total sample size in this case is 108, so you would hope that there would be some balance amongst all the cells depending on how they filled it out, whether they have any one of the 4 levels of insurance, and whether they're males and females. We would hope 108 divided by 8 that there will be some type of balance between all the cells, but you won't always get that equal numbers, which is fine. The ANOVAs are typically robust to those what would be a minor violation. And the dependent variable is normally distributed, and we're going to test that through looking at the stem and leaf plots. Okay, so we're testing for the homogeneity of variance between the groups. We want that to be non-significant, and that information appears in the SPSS layout. Here's a stem and leaf just to determine the frequency and that there is some type of normal distribution. And then here's just our basic descriptive statistics. So for males who had insurance, no insurance, their mean number of visits were 1.5. If they had private insurance, there was 3.3 visits, Medicare 3.3, and TRICARE 3.1. And then you can look at the females, and then you kind of have the same layout. So just looking at the descriptive stats is somewhat interesting. It looks like there's a difference between males and females. We can't say for sure whether or not these results happen by chance. Hence the reason why we want to run our parametric analysis to determine whether or not these results happen by chance. So once we plug all the information into SPSS, we get this layout, and it says it's a univariate procedure simply because we only have one dependent variable. If we had more than one dependent variable we're looking at, we'd run the Manova, and it'd be noted as a multivariate procedure. But if you look in the multicolored box here that I included, we're just looking at the 3 rows here, gender, and then insurance, and then gender by insurance. Gender by insurance is our interaction. If we look, there is a significant difference between the 2 groups based on males and females. Okay, so the number of visits, if you're a male, is found to be significantly different statistically, and based by insurance as well. But there is no significant difference in terms of gender by insurance. As you can see, it's non-significant at the 0.8 level. Okay, so we have to run our post hoc, and it really kind of tells us a combination of the different groups. So, and here you can see I circled important areas because there's a lot of repetitive information. They didn't code in SPSS, which you can do, or label. That first insurance was no insurance, 1 stood for none, 2 stood for private, 3 for Medicare, and 4 top of my head I can't remember. But in any case, instead of having your post hoc results just having 1, 2, 3, 4, you can label these in SPSS and you actually get the labels. So we're just looking at the combination between 1 and 2 at the top, and there is a significant difference, and also the difference between 1 and 3, that combination, and the difference between 1 and 4 was also significant. If you go down to second insurance, if we look at the combination, we already looked at 2 and 1, so 2 and 3, non-significant. Difference between 2 and 4, non-significant. And our last one we look at is the difference between 3 and 4, and that too was non-significant. So the best way to write this up briefly would, you would say something to the effect of, there is a significant effect of gender on the number of visits per year. So in other words, like I had said earlier, depending whether or not you're male or female, there seems to be a difference. And then using the descriptive statistics, you could see that women were having more visits. The parametric test didn't tell us who had more visits. They just said the differences between the 2, men and women. Those differences didn't happen by chance. Then when you look at the descriptive stats, It showed that women were, on average, visiting more than men. Okay. The second bullet, there's a significant effect of insurance status on the number of visits in a year, and the post hoc test showed that those with no insurance have significantly fewer visits than those in the other groups. So remember the differences between one and the other were all found to be significant. And again, you only indicate that they're fewer by looking at the descriptive stats. And then it didn't matter if there's an interaction type of insurance by gender. So in other words, it didn't matter if you're male or female. If you had no insurance, you were going to have fewer visits. Okay. But if it did find significant interaction, then it would basically say that depending if you're male or female and you had no insurance, then you may have fewer visits, but we didn't find those differences. So in our last question, we asked, post hoc tests are necessary for dichotomous variables. I think that's kind of easy. False. The dichotomous variables only have two groups. Post hoc tests are used to see which means differ from one another in cases where there are three or more groups. Okay. This concludes our presentation on Way Anova.